Okay, so welcome everyone for this week's Machine Learning Coffee Seminar. This week we have a really interesting talk coming up. So we have Miika Aittala from NVIDIA and Aalto University, who is going to tell us about Alias-Free generative adversarial networks. So Miika, please go ahead.
All right, thank you. So this talk is going to be about our semi-recent work called Alias-Free generative adversarial networks, which was published at NeurIPS last year, where it got an oral presentation. So this is sort of an extended version of what we presented there. And indeed, it's a joint work between NVIDIA and Aalto, and Tero is the first author. I'm the second one. Okay, so let's dive into it. So I assume everyone is at least vaguely familiar with generative modeling. So the idea is you have a big data set of something, let's say faces, but it can be anything. Faces are convenient as an example. And you train this neural generative model generator to basically convert random numbers into random instances of that data. And these random numbers are called a latent code. It can be, let's say, 500-dimensional vector. And now if you move around in this latent space continuously, you'll see the output change continuously also, and you can explore the latent space. And of course, people have taken this idea further. You can do things like find meaningful directions in this latent space, corresponding to things like facial expression and pose, for example. And now this opens the door for potentially animating these still images that you've trained with still images too. Now, there's a lot of things you can do. The details are not really important. There's a lot of research on this, but pretty much anytime you attempt something like this, you're going to see this very prominent artifact, which I hope survives the video compression here. So all the fine detail and texture appears to stick to the screen rather than follow the underlying motion. So if you look at the beard, the skin pores, all that stays in place while the face is kind of sliding underneath them. So what we do in this paper is we identify the root causes of this behavior and we fix it, and we get results like what you see on the right. So that's a little preview of the results, but let's try to now understand what's going wrong here. So in the real world, most things are built hierarchically, and they also move hierarchically. So for example, if the skull moves, that makes the eye region move, which makes the eyebrows move, which makes the individual hairs move, and so on. So GAN generators build the image in a loosely analogous hierarchy. So the generation starts from this low resolution feature map, which is shown here in false color. And you have these neural network layers, the convolutions, non-linearities, upsamplings, which gradually crunch the data and sort of break down the detail until you arrive at the final image. Then, for example, the eyebrows are built by locally breaking down the features around the eye region. And in principle, you'd expect that these finer features would inherit the exact position and motion of the cursor features they are built from. So, but this seems to fail in practice. So what's the problem? So it turns out that the networks are able to sort of cheat. So if the network has access to textual building materials from outside the hierarchy, for example, the noise inputs we use in these GANs, then you can simply use that to build the texture and ignore the detailed position of the feature data. But we don't strictly have to use those noise inputs. But even then, we might accidentally leak this kind of information into the maps. One mechanism is border padding artifacts. And then there is aliasing, which is the focus in this work. So the border issues are fairly easy to deal with. I'll briefly return to that later, but our focus is the aliasing, which occurs in the upsampling and non-linearity layers. So here's an example of aliasing artifacts arising somewhere in the middle of the network, let's say in an upsampling layer. So basically all upsampling methods used in practice leave traces of the underlying grid into the maps. So you can still see the sort of 2x2 blocks in the output that corresponded to the individual pixels in the input. And these kind of grid artifacts kind of live on in the generation. So it's tempting to think that the network would actually just learn to ignore these artifacts, but that's not the case. So quite to the contrary, the network really likes these artifacts. It eagerly amplifies them, even no matter how faint they are, and combines them across multiple scales to build the texture and detail. Because this is sort of an ideal building material in a way, because it's a regular, like a grid. You have all the frequencies from different scales and so on. Now that sounds fine, but the problem is that these grids are fixed to the screen coordinates. So they can sort of fade in or out locally, but they cannot move continuously. And any texture you build from this material is going to stick to the screen. So that's why you get texture sticking. Okay, so what can we do to eliminate this effect? So our strategy in this work is to prevent these artifacts from showing up in the first place. So let's sort of take a little step back and ask what we wanted in the first place. So when we move this low-res input to the generator, we want to see precisely the same motion replicated in all the intermediate maps and the output which are derived from that, with no other effects. So this property is called equivariance, and clearly if you have something in the output that sticks to the screen, that violates equivariance. So if we can somehow enforce equivariance, we would get rid of texture sticking. Now there's a lot of problems when you start thinking about how to actually do that, because well, first of all, this illustration was a bit of a cheat here, because we can only really move the low-res input one full pixel at a time, and there's only 4x4 pixels. So how do we even talk about continuous translations instead of these discrete jumps? Well, what if instead of thinking of the low-res maps as being blocky, we thought of them as being continuous blurry functions? So then there would be no problem in moving the low-res maps by any real valued amount. And this will sort of give us the language to talk about this equivariance. So next we'll develop this idea further and build this parallel continuous interpretation of the maps and the network. And that allows us to design equivariant layers in this continuous world. And then we can drop them into the style gun, and that should make the texture sticking go away. Okay, so let's begin by the first item. So I'll first change the visualization a bit here. So here's just some discrete abstract feature map. I'm showing positive in blue and negative in red. So instead of these blocky pixels, we'll just first draw this as this grid of Dirac impulses on the 2D plane with the unit square as sort of the region of interest. And we'll allow for some values to exist outside the square too for convenience, but we'll deal with that later. And here now the sampling rate corresponds to the notion of pixel resolution. So this would correspond to an 8x8 feature map. And if you have more pixels, then the points are just more densely spaced accordingly. So you have a higher sampling rate. So that's just a change in visualization. Now we rely on a fundamental result in signal processing called the Nyquist-Shannon sampling theorem, which states that continuous and discrete signals are equivalent under specific conditions. So to obtain a continuous version of a discrete feature map, the theorem allows us to interpolate it by splatting a specific interpolation kernel at every grid point. So mathematically, this is a convolution. Now, conversely, if we have a continuous map and we want to see the discrete version of it, we can simply point sample it at the grid nodes. So this is a multiplication with a grid of these unit impulses. So the requirement by this theory for this to play out is that the continuous version must be band limited to sufficiently low frequencies so that the grid is able to actually like capture all the peaks and troughs of this signal. So if you had too high frequencies in there, this conversion from continuous to discrete would not play out, and you'd end up with uncontrolled aliasing artifacts. And that's basically what's happening in the classical implementations of these networks. Now, so this, and of course, if you have a higher sampling rate or some higher resolution, that corresponds to having a higher band limit on the continuous side. So this kind of gives us this one-to-one correspondence between the continuous and discrete maps. So it's kind of a shift of perspective. So far, this is just a mathematical trick, like putting on these goggles that reveal a different but completely equivalent view of the world. So this parallel continuous world, sort of. So in practice, we must still use the grid to store and calculate on our finite computers because they use like discrete memory slots and all that. You cannot actually store a continuous function in the memory. But those discrete values are seen to encode the continuous function. So the continuous version is the actual substance of these maps, whereas the discrete one is the one we must operate with in practice. And now this will inform us as to what we should do in order to respect the properties we want in this continuous world, namely the equivariance. Okay, so now consider the sequence of operations inside our GAN generator. So again, it's just some long sequence of layers, and we are looking at it somewhere in the middle. Something's happening at each layer. So as established, every intermediate feature map here also has a continuous counterpart. So can't we just as well say that, for example, this operation F5 here mapped this continuous version to that continuous output? Or more specifically, if we have the continuous input, we can first discretize it and then borrow the discrete implementation of the layer and then interpolate it again. So this sort of establishes this one-to-one correspondence also between the discrete and continuous operations. So now you have this complete like correspondence, and this observation allows us to flip the setting on its head and actually think of the whole thing happening in this continuous world, and we are us designing the network on the continuous side and treating the discrete side as an implementation detail, really. So to figure out the practical discrete implementation of a continuous layer, we use this borrowing trick in the other direction. So we temporarily interpolate it. So what this all buys us is we can now finally require the equivariance we wanted. We can build it into these layers on this continuous side. And it actually suffices to make each operation equivariant in isolation, because it's sort of a transitive property. So to make that more tangible, here's an illustration of just some random continuous operation that fails to be equivariant. So if I move the input back and forth, you see that the output does move along, but it has all these side effects, these wobbles and all these that are basically the seeds of texture sticking. And indeed, if you look at the conventional implementations of upsampling, downsampling, and nonlinearities through this continuous lens, this is what they look like. So in contrast, this is what we want, perfect equivariance. So the operation does something, but its only response to motion is to exactly replicate that motion. Okay, so now with these tools, let's finally design the equivariant versions of basic CNN operations, upsampling, downsampling, and nonlinearity. And just to summarize the properties we want the equivariance on continuous side. We want still to be able to implement it with these discrete maps. And we must respect the band limit. We cannot introduce too high frequencies so as to not violate the Nyquist-Shannon theorem. So convolutions I'm not going to talk about because or the linear part of them, because they are actually already equivariant. that's a simple mathematical fact. You can look at the paper if you want the details. That said, strided convolutions are a programming trick, and they are not actual mathematical convolutions, so be very careful with those. But let's start with the first actual offender, which is upsampling. So this kind of fails to be equivariant in a way I showed on that slide. So what we are going to do is what I alluded to before. We are going to temporarily convert the discrete input into continuous representation and design the operation there. So we begin by interpolating, and in this continuous world, the right thing to do is actually to do nothing. And this is because we want to keep the information content intact and merely increase the sampling rate or resolution. And this happens at the final step where we discretize to a finer grid by point sampling. So obviously doing nothing is equivariant, so this fulfills our requirements. But how do we implement this in practice? So if we collect these operations, these terms, and simplify the formula, I won't go into details here. This boils down to the usual way of doing upsampling, but with this very specific kernel, which is of course familiar to people in signal processing, is the ideal sync kernel. In practice, we'll also need to clamp it to finite length, but I'll return to that later. So you just basically insert a 0 between every other pixel, and then you blur away the sort of the intermediate blacks. So that's the way to do upsampling in an equivariant way. So downsampling, that's also not equivariant usually. So let's try the same trick to fix it, and this is not going to work. So first go to the continuous world by interpolation, then maybe do nothing, and then resample it back to a coarser grid. Now this is illegal because we are violating a Nyquist-Shannon theorem here, and the problem is that we've sort of inherited high frequency content from this original input, and we are trying to cram it into a sparser grid, and you have two high frequencies there. So the solution is to delete the offending content by low-pass filtering here on the continuous side with this perfect band limiting kernel. So basically blurring it away. And now we are allowed to discretize again. And again, there is, and blurring is equivariant. It doesn't matter whether you blur first and move or the other way around. So this is also fine. And again, there's a practical implementation by first blurring with this ideal sync kernel and then deleting every other sample, which is classical. Okay, and the final offender is the pointwise non-linearity, such as leak ReLU. So let's again first go to the continuous side and do the ReLU there. Now this is equivariant, but unfortunately, again, we cannot discretize the result because we've introduced high frequency content along this clamp boundary here. So like before, we eliminate it by low-pass filtering, and we are free to discretize again. So this is a very subtle effect. Like you only see it if you boost the brightness by like 20x here. So you end up with these little ripples and all that you would expect. But it turns out that the networks are really able to latch on to even this amount of aliasing unless you do this properly. Okay, so that's the filtered non-linearity. But the problem here is that, and these are equivariant operations both, so that's fine. But the problem is, how do we implement this in practice? Because we can't really go to the continuous side with our computers, as said. Well, what we do is we approximate this visit to the continuous side by a single upsample and the downsample surrounding the ReLU. So that's sort of, instead of doing like infinite upsample, we do just 2x. And in practice, that's enough. So that's what we do. Okay, so now let's put this into practice and drop this into StyleGAN 2 and hopefully see texture sticking go away. We'll need to do a bit more after that, but let's see what it looks like. So here's a simplified version of the baseline StyleGAN 2 generator architecture with the noise inputs removed. So this is the only place we'll be changing. We won't touch the discriminator or anything. So in principle, we can just drop in the equivariant versions of the upsampling and values we just designed. But in practice, there's a few more things to consider. So on the right is our revised architecture, and the convolutions can remain as they are. We surround the leak value by a 2x upsampling and downsampling using the correct kernels. And if this coincides with the usual 2x upsampling, we can fuse them into a single 4x upsampling. We also use free features as the initial input to the synthesis network and add an explicit translation and rotation mechanism for the network to use. Now, to prevent those border artifacts I briefly mentioned, we maintain an extra border regions and gradually drop it away as the network progresses. So let's take a brief look at this region here. So running these large filters in an upsample resolution is actually very memory consuming and slow if you implement it naively with like the tools in PyTorch or TensorFlow. So we package these operations into a fused CUDA kernel, which performs the operations entirely in on-chip memory, and this gives us a drastically reduced memory consumption and up to 10x overall training speed up over this naive baseline. So we call this StyleGAN-free. Okay, so before we look at the results, there's a few more practical things I need to talk about. So speaking of those large filters, the ideal one is actually infinitely long, as I briefly mentioned, and it must be clipped somehow. So, and there are good ways and bad ways to do this. So with this, we'll analyze this in 1D because it's just a separable kernel. So with discrete filters on the left, we can analyze them using this frequency response plot. So this is basically the magnitude spectrum or the power spectrum of the kernel. So the idea is that we want to impose some band limit. We want to remove all high frequency content beyond some frequency, because anything that survives beyond the band limit will show up as aliasing later. So we'll want to, and ideally the infinite kernel would have this brick wall response where it perfectly cuts off the frequencies. Now, unfortunately, computationally, we cannot afford to have that many taps, and the less we use, the worse the approximation is going to be. And you end up with having this transition band where it goes from full response to no response. So you can identify a couple of regions here. These you might end up blurring too much, but that's not that problematic for us. I'll come back to that later. But aliasing is catastrophic for the reasons I've tried to explain. So we want to aggressively get rid of it. Okay, but what can we do? Well, we have a couple of more tools in our disposal. We can use windowing. So instead of just naively clamping the kernel, we can fade it out towards the edges. And that allows us to sort of control the width of this transition band and the presence of these ripples. So we use something called Kaiser windows. And we can also just vary the width of the kernel, how aggressively it blurs. And this sort of gives us a way to control the position of the transition band or the cutoff frequency. So as I said, our goal is to aggressively eliminate this aliasing here, and let's try to design a filter that does that. So the idea is that we kind of try to move this transition band to the safe side of the band limit, so nothing is left after that. And here's just how that filter might evolve when we find out the parameters. And we end up with this filter that has basically almost no response on the forbidden area. We do end up blurring too much, but that's not a problem in the intermediate kernels as long as towards the end of the network we allow it to create all frequencies. Because the intermediate maps are really just something abstract. And related to that, we also do this sort of a holistic redesign of the upsampling schedule. So before, you used to have this pixel-driven doubling of resolution every couple of layers. But really the more natural viewpoint here is that the network should sort of increase the bandwidth as it progresses. And instead of sampling rate determining the bandwidth, it should be the other way around. So here's the classical StyleGAN2. So as you progress, your resolution doubles every 2 layers. So that's the log resolution. But instead, what we want, or what we do, is we specify this geometric growth for the band limit we want to impose, and sort of the transition band breathing room around it. So this gives us a nice, smooth progression of what actually matters, the effective resolution through the frequencies we allow to be present in these maps. Now to determine what sampling rate can support this, we just round it up to the closest power of 2 to get the grid resolution. But that's really a technical detail. As I said, what really matters is the amount of frequency content. And towards the very end, we allow for some aliasing because that doesn't cause texture sticking anymore, but actual data does have some aliasing. So we'll squeeze out the blur sort of at that point. Okay, so let's evaluate this a bit, just very briefly. So if we go and translate the input to basic StyleGAN2, we do get motion back and forth. But we also get this serious texture sticking. You see the hair sticks in place and all that. There's an alternative visualization where on top of that, we move the output to opposite directions. So these should perfectly cancel each other out if this was properly equivariant. And here's the amount of error you are making here, because clearly that is not being very equivariant. So I won't go into detail here. We have extensive evaluations in the paper, but as we introduce these changes I've listed one by one, we gradually drive down this error in equivariance until we arrive at something that's almost close to like machine precision in terms of this equivariance error. Or we could go there, but in practice it's not needed. So in practice, we have perfect equivariance now, or translational equivariance. Okay, so there's one more small space there on the bottom right. So one more thing would be, what if we didn't ask only for translational equivariance? Well, what if we wanted also rotational equivariance? Well, let's see what happens if I try to rotate the input to the network continuously. So this kind of fails badly with this translational network. But we can actually make the network rotationally equivariant by a simple change of using 1-by-1 convolutions instead of 3-by-3, because these are sort of not sensitive to orientation at all. So they will just pass the orientation through unchanged. Also, you use slightly different kernels in the upsamples and downsamples to be radially symmetric. And with this, we get very good rotational equivariance. It's sort of surprising this works in practice. So we leave this as an optional variant of the network. So we have two deliverables. Sort of one is the translational equivariant network, and the other one also has the rotational equivariance. They have somewhat different properties. It's an interesting thing. Anyway, so with all these pieces together, let's look at the resolution. Resolution results. Okay. So the generated images are in general similar quality to the baseline StyleGAN2, but the texture sticking is gone when you apply it to motion. So this is again the same example you saw earlier with different faces. And by the way, we've used this new unaligned version of the FFHQ dataset for this to highlight the difference. So applying this new architecture on the right to an unaligned version of the MET faces painting dataset, and just do plain old latent interpolation. See this interesting effect that the paint strokes now naturally follow the motion of the underlying faces rather than sort of stick to the canvas. So it's an interesting creative effect potentially. So of course, cats and dogs. So with the AFHQ dataset, we see that the fur of these animals now follows the geometry properly underneath, instead of being sort of this layer of detail that sticks to the screen, as you see on the left with Stargan 2. Now here's a more exotic data set with beach images. So the Alias-Free variant on the right shows a very different motion behavior, where it kind of looks like it's the camera is rotating and zooming and panning into the scene rather than sort of boundaries of these regions just moving around. Now in some pretty fascinating emergent behavior, we see that the internal representations the network uses, so those intermediate maps that we've been talking about all along, are very different with this equivariant architecture. So the top row is the basic Stargan 2, or the baseline Stargan 2, and the bottom 2 rows are the 2 variants of these equivariant networks. So it seems, because we are kind of denying it any information about the like absolute position of anything, and we are not giving it a grid basically to build the image with. It seems that it has to invent its own, so you get these sort of cybernetic like basis maps of the geometry just spontaneously emerging in the internals. All right. Joint limitations. One thing to watch out for is that if the training data itself is aliased, either by accident or design, this kind of an architecture will have a hard time reproducing those artifacts, and then the training won't go well. So this might happen on purpose in let's say pixel graphics, where the key part of the aesthetic is that you see these blocky pixels, but the network has no reference about where the blocks, how to place blocks exactly, and that's just not going to work out. The discriminator catches on immediately. And, another one related thing to watch out for is something like the letterboxing, like the black bars above and below your images, for example. The network will really struggle to place them properly, and that's actually going to make the training fail. We've seen this happen because, yeah. All right. So we do also see some symmetry artifacts, some monotonous textures. So, for example, here we have a middle tooth on this person, and you see the texture on the other example is kind of repetitive. This is probably related to the fact that we had to remove the noise inputs. So it doesn't quite have the same source of entropy to generate a random texture. So it sometimes ends up as more monotonous. It's a good question of what would be an analogy to the noise inputs in this equivariant world. We don't really know what the answer is to that. So that's for future work. Now, you could also, of course, ask whether there could be similar effects to be had with further equivariances like scale or just general image warps and so on. Now, there's a lot of research on this taking advantage of this in like the group equivariant CNNs and so on, which is very interesting, but it has a different perspective. Sort of, it comes from data efficiency and efficiency of these representations and so on. But it's a good question if they would have, if there could be similar image effects related to those. And we also targeted some basic building blocks of CNNs. The resamplings, non-linearities, they are used all over the place, and so it's interesting to ask whether you could have similar benefits in some other generative or even other like tasks, like let's say image-to-image translation. Okay, so we expect that this work opens up many new and exciting possibilities possibilities for the use of GANs in synthesizing video and animation. You can try it yourself. We have code and pre-trained models available online at the project GitHub page. And also some interesting stuff like easy to use visualizer that you can use to just out of the box generate images from these pre-trained models and look at the internal representations and try out the Equivariance stuff with all kinds of scrubs and so on. Okay, so there's the address, and I thank you for your attention.
Okay, thanks a lot for a very interesting talk. Any questions? You can either raise your hand or write in the chat. Okay, so while the audience thinks, so I have a question. So I wonder, sort of, could one actually think of the resolution and pixels completely as a nuisance? And could one imagine a system where you don't actually have a resolution or pixels at all, where everything is just continuous fields?
Right, yes, this is a good question. And there are architectures that do something like this. So basically that would be like implicit generation, like where you input the X and Y coordinate and it gives you the value there. So especially this one-by-one architecture we have, it's kind of a step towards that direction. But because now you're in principle already only combining stuff within single location. And the only thing there that ties these pixels together is the upsampling, so sort of the low passing caused by this upsampling schedule. But yeah, there are papers that do this. We cite them in this paper also, if someone's interested. The problem with that approach, when you don't have a notion of like a band limit, either through this explicit band limiting or through the resolution, the pixel resolution increase, is that you don't really get this natural coarse to fine refinement necessarily, because it's immediately able to jump to doing the very finest details. It can't really avoid that. Like let's say you have at the very lowest resolution, you are inputting this very smooth map, or this smooth sort of input there, and now you put it through a ReLU, so it's going to look like a sharp clamp there. So you end up with this thing that's very smooth and very sharp at the same time. So, and that just doesn't seem to be, well, that leads to problems in the generation, because it then you kind of have this very, very sharp edge there, and you start piling them together, and you end up with this sort of level set artifacts and all that. So I would argue that having this notion of increasing resolution is actually very useful, because it melts those things away. So, and it naturally gives you this coarse to fine progression, where you first do the big features and then you break them down.
Okay, definitely makes sense. Any questions? Okay, so it seems that there are no questions from the audience. Everything was crystal clear. Presentation was super clear. So in that case, I want to thank the speaker for a great presentation. Also thank the audience for your attention. And we will. Okay, we have one question came up. So what is the lowest resolution you have worked with successful generation of images from Mastana?
So what do you exactly mean, like a lowest resolution, as in lowest output resolution, or the input resolution? Or of course, I mean, you can do as low as you want. Your images are just going to be very boring if they're 16 by 16 or something. I mean, that's super easy to generate, obviously, but maybe you meant something else.
So does that answer your question?
Yeah, lowest input resolution. Right, so are we talking about something like a translation image-to-image translation where you want to change one kind of input to another kind of output? Because here what you are doing, you are basically just feeding random low-res data at the input. So
yes, well, for example, actually, so like for some of our inputs, like the images, they basically actually like had the quality of almost like a 256 actually pixels, you know, and still basically there was actually a lot of kind of like actually, so for example, like the blurriness, you know, inside actually like the input image data set, as well as a lot of actually sort of discontinuities, you know, as you also mentioned. And actually, so then because of that, then well, obviously, basically, then we had actually then used the case of StarGAN2, the quality of the generated images, you know, they were not really actually basically actually kind of like as satisfying, you know, as the case of, for example, like this kind of the sample, like the cat and dog data sets, you know, or for example, like the case of the face images. And actually, so then because of that, I was actually kind of like wondering that, you know, so then basically what would be basically like for the case of the lowest like the resolution of input images, you know, that can probably actually like give us, you know, a kind of like a satisfying image quality at, you know, at the output.
Sorry, the audio quality was a bit low. I didn't quite get the beginning of that, like what the setup was. So it is on this image-to-image translation, you mean?
Yes,
like,
yes,
yeah.
yes, yeah.
Yeah, we haven't really done that much image-to-image translation ourselves. So we are usually kind of considering this full just full like a unconditioned generation case. So I can't really say say anything too specific on that myself, other than there is of course a lot of research on using StarGAN for that. Yeah, I probably missed some part of your question because the audio was kind of.
Thank you.
Yeah. Well.
Okay, and it seems that we also have one more question from Jarno Seppänen. What about making the discriminator also equivariant? Yeah, that's another good question. It's kind of related to this question of whether these primitives would be useful also in like discriminative tasks in general. There are actually papers on that. We also refer to cite them in our paper. Yeah, that could help with some of those artifacts you see, like the symmetry artifacts and so on, for some subtle reasons. There are extra challenges that come up when you go to the other directions. Also, like instead of doing the generation where you expand the maps, you are doing a contraction. Because now the boundary effects are also kind of difficult to deal with. You get failure of equivariance because of that, because the network is always able to sort of sense how far the edge is and sort of use that to cheat. So you might the aliasing might not be the primary issue there, and you might not get as significant a benefit in applying these procedures on the discriminator side or discriminative side in general as for the generative. But yeah, there could be ways to deal with that, and we haven't really looked at it. I don't know what the answer is potentially, but yeah, we do attribute potentially some of these problems to the lack of equivariance in the discriminator. Let's say also that monotonous texture might be caused by this fact that the discriminator sort of has this kind of looking at this grid like this regular grid, but your texture can sort of deform, even though it's like monotonous, it can be curved and so on. So for that grid, it might look more interesting than it actually is when you. So it's possible that an equivariant generator would better be able to tell if the texture is monotonous and do something about it. This is a hypothesis. I don't really know. Okay. So I think we are now ready to close the session. So I again want to thank the speaker and the audience, and we will come back next week. Okay, so have a nice day, everyone. Goodbye.
Bye. Thank you.